Hi again. Welcome to another episode of our weekly Ask Me Anything virtual office hours where we discuss all things big data. Today we're going to discuss a very hot topic, which is, in very simple words, how do I get my Elasticsearch running in production, squeeze every bit of performance from it without risking stability. So our customers reach out to us with Elasticsearch stability issues quite often, to be honest. This is something we do quite a bit. And by us, I mean Big Data Boutique. My name is Itamar. I'm the CTO and founder. And we basically do big data projects, consulting, hands-on development, you name it. And we do a lot of Elasticsearch projects as well. So our customers are trying to find a way to make their Elasticsearch clusters working. And to be honest, more often than not, we find they had some configuration errors, and it's quite easy to have that with Elasticsearch. Definitely, if you're just trying it out and didn't go into depth on exactly what it does and how it's working. So today's session is about those types of errors. I'll go through the common issues we see our customers are having and also show you the common things we tell them to fix and what types of things we do with them. By no means this is going to be a comprehensive checklist, so I'm not going to cover everything. And there is quite a bit that we won't be discussing today, but for many of you this could actually be very, very useful. So Big Data Boutique and the team that I'm leading here is pretty much the best Elasticsearch consulting and hands-on development team you'd find. We are providing consulting and hands-on development, performance and cost optimization services, managed services around Elastic, as well as training our developers. Some of our team are actually Elastic certified engineers as well. And we've been working with quite a lot of big names in the industry for the past 8 years or so. So we'll begin today with talking about the typical issues with Elasticsearch in production. And then we'll go through some recommendations around cluster topology and a couple of additional things. And then we'll discuss the usual suspects that we are going to first look at when we come to handle those kind of production issues our customers are having. So this Ask Me Anything format, just a reminder, is a format where we are going through a topic relatively quickly, so about a 20-minute presentation, and immediately after that there is a Q&A open for all. You are welcome to participate, ask any questions you may want, and we are going to use the chat over here on the YouTube, under the YouTube video, and feel free to post your question over there. And immediately after the session, I'll go through the questions and answer them. So let's begin. With Elasticsearch or the Elastic Stack or ELK, which you probably have heard of that in different names and terms. Elasticsearch is the main core engine that drives the entire Elastic Stack. You are maybe probably using Kibana for visualizing data, showing dashboards and visualizations and maps and doing quite a lot of things. So quite recently, the SIEM solution that Elastic has brought to the table in many such applications and use cases. So Elasticsearch is the core underneath those Kibana dashboards that you're going to use. So everything Kibana is doing essentially is backed up by Elasticsearch features. Elasticsearch is the cluster, the multi-node, most likely installation that is going to hold your data, and this is what is going to accept the queries and execute them. So that is the part that you really want to have stable. And oftentimes our customers complain about node disconnections, so nodes just disconnecting from the cluster. Stability issues, even maybe without disconnections. So clusters just hanging, or nodes in the cluster hanging, maybe some nodes that are crashing or going through restarts, or just general slowdowns. So for example, queries that are going to run very slow, queries that are going to time out. If you're using Kibana, you would experience that as a timeout in Kibana, or dashboards taking forever to load. Some cluster management tasks, like for example, creating an index, updating a mapping, deleting an index, just viewing what indexes you have on your cluster, are also sometimes very slow. Today, in modern Elasticsearch versions, some split brain situations where this is becoming more and more, let's say, rare to see those, but those can still happen. So split brain is the place where you can actually see your cluster running in two different clusters, let's say. So there is two different clusters, and your cluster has basically been split into two, and that usually leads to data loss and corruption. And even the general complaint about, well, my cluster just ran very slow, or wasn't able to handle the load, so we just throw some money at the problem and added more nodes, or scaled up the cluster, used bigger nodes, and for us it's working now, even though we are paying quite a bit on hardware for that. So that's also a very common complaint we hear, and hopefully today I'll be able to show you a couple of things you can look at your cluster and maybe even fix. So as most of you probably know, Elasticsearch is built and written in Java and is running on the JVM. And as such, Elasticsearch is quite a happy user of the Java heap. It has a lot of data structures, a lot of objects that are being maintained by Elasticsearch on the Java heap space, and that essentially has some implications. For example, you are limited with how much data you can use with Elasticsearch if you're using the Java heap space, only the Java heap space objects. Since you are on the Java heap space, there's GC, garbage collection, involved that can slow down some operations. It can show very high CPU clocks, and there's quite a bit that's involved there. So as the older versions that you have for Elasticsearch, the bigger the issue, or the more pain you are going to feel with the Java heap type objects. Elasticsearch is using that for quite a lot of things, for caches and global ordinals, which are data structures that are being used by some aggregations. Quite a lot of small data structures that are important to the operation but are not the big deal breaker, and probably the most famous ones are the field data data structures, which historically have been the default for Elasticsearch, and then Elasticsearch over the years, since version 5, made those actually disk-based, so are basically taking that off heap. And essentially Elasticsearch are trying to do this to as many data structures as they can. Last week, Elasticsearch 7.7 was released, and one important data structure that is very frequently used has been moved off heap as well. Something that is relating to the _ID field, the document IDs. So Elasticsearch are doing quite a lot of work with that. And as long as you're staying on a current version, you're probably going to suffer less than Java heap problems, but still you may be making some mistakes over there. For example, setting the heap size too large. So over 30 gigs, that is definitely an error. Over 50% of the memory you have on the machine, that's definitely something you shouldn't do. Essentially, usually we're going to recommend using a low number for the heap size to be used on modern Elasticsearch clusters, mainly because this is going to, in a lot of use cases, you're going to use the disk more often than you're going to use the memory. So that would be one thing to note, and one thing that actually damages a lot of clusters, affects a lot of clusters. So if you're seeing out of memory errors in your nodes and things like that, that could be the issue. Another common mistake that we see is the way that the cluster is deployed. So this is the recommended cluster topology. So the recommended way to deploy Elasticsearch on whatever platform. Your application should be deployed and talk to nodes in the cluster. Now, this is a very common misconception. A lot of people know about data nodes and master nodes in Elasticsearch. Data nodes are the nodes that are going to hold your data. Master nodes are nodes that essentially, ideally, are not going to do anything. They are only there to maintain quorum, to make sure the cluster is well defined. So that essentially means just being there and pretty much doing nothing. And one of those nodes is going to be responsible for maintaining the cluster state. So any change you're going to make to the cluster is going to have to be approved and ordered by that specific node, which is the active master. Now, a lot of people think that when you make things with the Elasticsearch cluster, for example, when you write data, you have to go through the master, and that is not true. Only cluster metadata updates is going to have to go through the master node, but not every request. This is why you shouldn't really dedicate any efforts or any resources to the master nodes. You should, in fact, not even direct requests to them. They should just be in the cluster and let them do what they do, and your requests should really only go to that data nodes. And data nodes are the nodes that are going to have a lot of resources, a lot of CPU, a lot of memory, and those are going to handle your requests, your queries, your indexing requests, and so on. For large clusters or clusters which are going to have a lot of throughput coming into them, we also recommend adding client nodes, or also known as coordinating nodes. So nodes that can basically be delegated the HTTP handling and the request handling and handling the queries and things like that to basically offload some work from the data nodes and allow those quite pricey nodes, pricey machines to do their work in an optimal manner. Elasticsearch 7 also introduced the concept of voting on the node in terms of master and master eligible nodes, but since we do want to have some way of falling back to a master, to have an active master if the active master is decommissioned or crashed or something like that, our recommendation is to have 3 small master nodes and the rest of your cluster just execute requests against that. And again, do not send requests to master nodes. So that's a big misconception. A lot of people deploy master nodes and direct queries directly to them. Actually, even more people deploy Elasticsearch clusters without separating master and data nodes, and that is basically the root of a lot of issues with Elasticsearch clusters in production. We just discussed cluster topology and metadata. Let's talk about data. So your data is being persisted in indexes in Elasticsearch. Index is the name for that pool of documents that you can query and put data into. And a lot of the issues that we see with Elasticsearch also pretend to indexes, to the actual data and the way that data is persisted in Elastic. For example, mapping issues. Since Elasticsearch is so-called schemaless data store, meaning you don't have to define a mapping or a schema, Elasticsearch will define it for you. It makes things maybe a bit easy, but for every real deployment, every real use case, you really do want to define the schema yourself up front, like you do with non-schemaless databases. That is actually the right practice to do. whenever people are leaving the default mapping as is and just using it, that basically blows up the index, slows down indexing, and has a lot of issues with it in large deployments. So that is something you should really avoid. There's many other mapping issues we see. Just make sure you understand what the mapping is doing, what type of fields you have there, what types of fields you can use, and make sure you are optimizing on that. Another issue we see with indexes is incorrect sharding strategy. For example, using the routing variable. If you know what it is, our recommendation is not to use it. There is better options nowadays. Or just having way too many shards on the cluster, many small shards and things like that. You should really consider your sharding strategy, making sure you have as few shards as possible and as needed. And that will really help your cluster stability and also responding to queries on a timely manner. On that note as well, index life cycle. So when are you going to roll to new indexes? When are you going to remove indexes? How are you going to remove all data and do data retention? So all of those things to consider are also, if you do this incorrectly, you can get to a point where you have some performance penalties. For example, if you're doing TTLs or retention, removing data using delete by query on indexes, you're just going to delete documents to remove them instead of just dropping an entire index, for example, using time-based indices. That would actually have a significant performance hit because Elasticsearch really doesn't like a lot of updates and deletes to indices. Another thing we often see is people trying to enforce the relational mindset on Elasticsearch. So that's true for every non-relational data store, to be honest. But with Elasticsearch, we see it quite often, probably because Elasticsearch is very popular, and a lot of notion comes from the idea that, well, SQL is bad at something. Let's try Elasticsearch because everyone is saying it's really, really fast, and then they are just trying to use that same UML diagrams and models on Elasticsearch. That wouldn't work, and by that I mean things like the parent-child modeling, or it's called joint field nowadays, nested documents, those kind of things. You should really try to avoid them. In some cases, it would actually make sense to use Elasticsearch and still have nested documents and some types of relationships between documents, but it is very unique set of use cases, and generally you should try to model your data using document-oriented modeling. For example, using domain-driven designs, aggregate root concept, and things like that to get to a point where a single document represents an entire entity without any strong relationship with other documents or indexes. So enforcing the relational mindset on, or trying to put a relational data model into Elasticsearch will just not work, and it will cause a lot of pain. Elasticsearch isn't transactional. Elasticsearch has different consistency guarantees than SQLs, and so on and so forth. It just wouldn't work. Continuing on the previous note that we had on the index life cycles, hot, warm, cold architectures is actually something that can help you in a lot of cases. So if your pain is with costs, try maybe using stronger nodes for indexes that hold your recent data, or indexes that are actually actively indexing data, and then using other types of nodes with larger data densities, so a higher ratio between storage and memory and compute, and use them for persisting the majority of your data, and then having stronger nodes for the indexes that you're currently ingesting to, or indexes that you are going to quite frequently query or execute harder, more demanding queries. There is also the concept of frozen indices, which is relatively new. It is something that allows you to basically persist data and not even spend a single byte in memory for it. And if you need to query, the querying is going to happen entirely on disk. And it is also something that might make sense for clusters that need to hold a lot of data, but 80% of it isn't being queried maybe at all, maybe once a year. And you can't really, and should have that available, and you can have that on just a backup. So frozen indices and large data density, what we call cold nodes are going to be a good solution for that. Now, the first thing that we do whenever we approach any type of customer having any sort of issue is making sure we have good, proper monitoring in place. Now, if you're on a modern Elasticsearch version, you already have XPack monitoring, which it can already monitor your cluster out of the box and give you quite decent dashboards and metrics and graphs. It lacks a bit. It's a bit hard to use. It doesn't show a lot of things which we would like to see. For example, multiple nodes on the same graph and various metrics that the data does exist for them, but you can't really see them. So what we did, we created our own Grafana dashboard, which can basically depend on the XPack monitoring data, so data collected by XPack monitoring, which you have built in since somewhere in version 5 even, and it's free to use. And in the repository, you have here, on the link here, we also list that on the video notes, you can find a Python script and a Docker container, which basically mimic the way XPack monitoring collects data and sends it to Elasticsearch. And you can use that instead of enabling XPack monitoring, and that would basically allow you to also enable monitoring without doing any type of cluster restart or things like that. The reason why this is pretty much the first thing that we do is because oftentimes there are things that we can just spot on the spot. We can just see something and it will shout at us, but more often than not, we will need to see the behavior over time. For example, understand what is the load average for the nodes, how it behaves, how much CPU is being used, what is the frequency and the spikes of indexing and query operations, how much the disk is being used, how does the GC look like, and things like that. We are mainly looking, to be honest, on two things right away, which are thread pools and cache usages, so cache evictions and how much cache is being used. Thread pools is going to point us in how much under-provisioned or over-provisioned your cluster is in terms of CPU. And caches, so how much cache is being used on memory and how many evictions there are for the types of caches are going to point us on how much memory you need to add or how much over-provisioned you are in terms of memory. Now, those can also point us at configuration options that we need to change, and these also various types of configurations we can fine-tune, and that is definitely possible to do. Unfortunately, not if you are in a hosted version of Elasticsearch, but definitely if you are self-hosting or have someone manage the cluster for you on your cloud or on-premise. What you see here, for example, is two interesting things. So there is high usage of field data, which I mentioned before, that usually points at things like high global ordinals usage or just using the good old field data instead of doc values. That is something that just pops immediately, and we are just going to check what is the root cause of that and try to see if we can avoid having 6 gigabytes of heap memory per node if at all possible, or just try to improve on that. And you can also see the request cache has some sort of a plateau. So it is capped on a certain percentage of the memory assigned to each node. And in this case, like you can see here, we can clearly see there is a plateau. So the request cache could have used more memory, but it doesn't. So once we install monitoring, we can spot those things immediately. And by, for example, in this case, lowering field data usage and giving more room for the request cache, we can basically reduce the amount of GCs happening, boost performance for many types of queries, and also reduce the number of evictions, which also affects GC, CPU, and slowness in general. So one of the things we do, other than just doing those kind of things for active clusters, is also helping large customers with big clusters or clusters that are going to be deployed on-prem for various customers. We'll help them figure out what would be the right capacity or what would be the right size for their Elasticsearch clusters, depending on the usage. Some customers are going to have write-heavy indexes and clusters. Some are going to be read-heavy. Some are going to do full text search. Some is going to use Elasticsearch for aggregations and dashboards, BI, those kind of things. So depending on your use case, we can figure out what would be the right capacity, the right cluster size for you. We have a fully automated suite that allows us to just execute 20, 30 permutations of clusters on your infrastructure, Kubernetes, AWS, GCP, Azure, and a couple others. And we are able to execute those in parallel. And after a few iterations of that and seeing the reports that those runs generate, we can show you what size of a cluster, what size of a node, what types of configurations, those kind of things are going to be best for you. And then we can allow you to do the right trade-off between cost, performance, and so on. So that's a service that we are offering, but it's all powered basically by those kind of advices and toggles that I showed. That is pretty much it in terms of content. And now it's time for us to move for the Q&A. So let's start with the Q&A and reminding you any question that you might have, you can send on the chat here under the video on YouTube, or you can send us to us via email or ping us on Twitter, and you have all the details here. And we already have 2 questions. I'll start answering them, and if you have any more questions, just send them out. So first question is about GC. So I mentioned GC. Matt is asking about types of GC. What is the G1 GC, and is it recommended to use, and how useful it is? So GC is the garbage collection for Java, and historically it's been designed to collect small heaps. So small heaps basically mean let's say 8 gigabytes or even less than that. And the way that algorithm works is by basically doing a very costly operation that what we often call stop the world GC. So everything just halts. Elasticsearch doesn't have any threads available to it. The JVM will do the GC sweep. It will just find all the objects to collect and it will free them. Only once the GC operation is being completed, then Elasticsearch will get back threads and be able to continue working. Now, that GC is going to be slower and slower as you use higher JVM heaps. This is why we don't recommend using 20 or 30 gig of heaps in general. But this is also why a lot of people are interested about G1 GC. G1 GC, Generation 1 GC, that is the more modern GC algorithm that allows JVM to collect objects on the go without having this stop the world behavior. And up until I think about 2 years ago, Elasticsearch didn't support it because Elasticsearch does quite a lot of tricks with the JVM and swappiness and memory locking. So the recommendation is indeed to try and use G1GC. It will sometimes improve things, sometimes actually the old type of GCs would work even better or allow for more stable operations. Our recommendation, to be honest, in most use cases is to use 10 to 15 gigabyte per data node, especially if you're doing aggregations, and then have the rest of the memory, even if you have 64 gigs of memory on the node, that memory is not going to go to waste. It will just be used for the off-heap data structures, and specifically be used by the file system cache to do a lot of interesting things. So that's about G1GC. It's supported on recent versions of Elasticsearch. You need to be above some version. I think it's somewhere in 6.5 or 6.6. And you need to be on I think over JDK over JDK 11. So that's about G1GC. So Kobe asks, using Spark to load daily data to Elasticsearch, about 1 terabyte of data. We load the data to a new index that should be available for queries right after ETL execution. Can you please provide tips for indexing speed improvements? So I can tell you 2 things about that. Elasticsearch, to improve indexing speeds, you basically want to have more shards. So the more shards you have, the more CPU and cores you can spend on indexing. So you can have more indexing happening, and you can also spread that across many nodes. The problem with shards is that in the long term, if you're persisting that data later, in the long term, more shards, if they are on a smaller scale, more shards are going to be more costly for you to operate, and also overload the cluster metadata. So we don't really like a lot of small shards. We like bigger shards, especially for the aggregations use case. So to speed up indexing, you basically want to have more shards. That's the basic advice. However, before you do that, you can first try to understand why your indexing is not at the speed that you want. Take a look at the indexing or write or bulk, depending on your version, thread pools. So look in those thread pools, you can maybe see if you are indeed under provisioned on the CPU in terms of indexing. If you are, well, maybe sharding is a good way of doing that. Maybe your bulks are not optimized. A lot of times mapping has a lot to do with that. Are you using the default mapping? Are you optimizing your mapping? Writing doc values for fields that you don't have to have doc values. So disabling doc values on some fields can greatly improve your performance and things like that. So there are quite a bit of things that you can do, quite a lot of optimizations, but I would start with looking at the thread pools, looking at your mapping, trying to optimize on that. And as a last resort, you can always use more shards and more nodes, obviously. So spread the indexing into more nodes and more cores. And if you want to then shrink back the index to less shards, you have the shrink API. Maybe you can have you can do re-indexing and offline asynchronously, things like that. So that would be a nice solution. So just general advice, but again, there's quite a lot more that can be going on there. Hoping this helps. Khalil asks, I'm quite new to Elasticsearch. I wanted to know what's the best way to manage ES cluster like snapshots. I'm not sure I understand. If you mean backups, then you have a very simple API for that. Elasticsearch versions 7 and up also includes snapshot lifecycle management. So it is completely, it can be completely automated from Kibana and managed by Elasticsearch itself. Also on the free tiers. And before Elasticsearch 7, it's quite easy to do that. There's quite easy APIs for snapshots. And there's also a utility called Curator, which you can use to even simplify that. Dali asks, are your Kubernetes nodes ES dedicated, or you don't mind to run mixed load on nodes? So actually on this channel, on this YouTube channel, I think it was 2 years ago or less, I had a talk about Kubernetes, which was recorded, running Elasticsearch on Kubernetes. So the answer to that is quite not simple, let's say. If you have a significant workload, I would definitely advise you to not run Kubernetes. That additional level of abstraction, I think it will just complicate things for you. For example, node affinity, things like that. I think it's going to be much more involved and also perhaps even reduce the amount of performance you can squeeze out of it, because, for example, Kubernetes will automatically take something like 20% of your machines for its management. So why pay for that if you can have good automation, good deployment on just plain vanilla machines? So for significant workloads, it would be much cheaper and I think much easier if you do this correctly to run on actual VMs. So EC2 and Google Compute and so on. In some cases, it is actually for example, on-prem deployments, things like that, Kubernetes makes sense. So again, if that's significant workload, I would use dedicated nodes probably to make the most use of those nodes. But I don't mind running mixed loads or nodes, especially on the smaller clusters, which are the place where I would originally use Kubernetes for running Elasticsearch. If I want to have many small clusters, Kubernetes is perfect for that. So that would be the main driver for me to deploy Elasticsearch on Kubernetes. Another question we got, are client nodes a must? So I showed client nodes in the cluster topology, and I showed it as part of the cluster topology, and indeed they are not a must. They're not something you really have to run. It is something we say it is recommended to run on some scenarios. For example, like I said, when you have really high throughput for your data and you want to make sure that that throughput is actually being maintained, and you want to make the most use out of your data nodes, and you don't want to pay, for example, if you have local SSD on data nodes, so you want to make the most out of that CPU, or you want to scale out and scale down automatically, auto-scaling on that CPU, then you can deploy client nodes. It's not a must, but on the larger types of clusters, you'd actually see a lot of performance benefits out of that. Another question. It will sound a bit off topic, but I'm working on building applications which will be used for searching articles based on keywords. Do you recommend to use Elasticsearch? What would be the alternatives to Elasticsearch for the solution? I'm not sure what you mean by search by keywords. If it means full text search, so Elasticsearch will probably be the best tool that you can find. Elasticsearch and Solar are the leading text search engines, and I don't think you should be looking for anything else. If the question is about Elasticsearch or Solar, my personal preference is for Elasticsearch, mainly because it's much easier to handle, much easier to maintain. It's much easier to squeeze every bit of performance out of. I think the problem to be solved is related to full text search, fuzzy search. So Elasticsearch is definitely your solution here. An alternative would be Solar, but like I said, I think Elasticsearch is way superior. A follow-up question about ingestion speeds. What is the recommended size for shard? That's a good question. I don't have like strict numbers. Nobody will basically give you any. But for ingesting, there is no, in terms of recommended sizes, right? It's just a matter of how much CPU you can use. For the long term, when you want to actually query that, I would say there are 2 or 3 factors you need to take into account. So the first one is what would be the use cases. If it's the search use case, you should look at the number of documents, and you should favor, I wouldn't say low, but let's say let's keep on the millions, because if each shard is going to have more than a few millions of documents, you will see search speeds going down. It would really depend on your use case, what you're doing, but over the years, the types of performance testing we've done showed that the sweet spot is somewhere around that. And that basically has to do with the way Elasticsearch scores documents and things like that. Assuming, again, you want to have scoring. For the aggregation use case, we actually prefer larger shards, because that's some sort of a columnar storage that's being used there. And I'm only talking about the more modern Elasticsearch versions, not older ones. And in that case, you actually want to have bigger shards, because performance is going to be much more significant, and it will still depend on the cardinality of fields you're going to execute your queries on, but still it will still favor larger shards. Now, problem with larger shards, it's maintaining that, and cluster elasticity. What happens if a node goes down, or that index and those shards need to be reassigned? So we usually recommend not having too big of shards. So I don't know, 10, 30 gigs of shards would be a good number. You can also go beyond that, but you should just make sure you're covered in terms of moving shards around if that happens. And for the storage density case, we can even talk about 200 gigs of a shard. That would be, I think, some sort of a maximum in this case. But again, it will really depend on your use case. I wouldn't go for too big of shards. But if you're doing aggregations, I would definitely try and have more gigabytes per shard, as opposed to, for search, somewhere around the millions of documents per shard. Seems like we are out of questions. So thank you very much for all. Feel free to reach out via email, via Twitter. Look up at our blog. There's quite a few interesting pieces there also about Elasticsearch. See you next week. We're going to talk next week about some big data topics and schemas and file formats. And feel free to suggest some more topics for our future sessions. Thank you very much for your time, and see you again soon.